Welcome to the session number 7 from the playlist of Heat and Thermodynamics. The topic is the thermal expansion in solids, liquids and gases and the change in their density due to this thermal expansion. So the first point is the solids experience the linear, superficial and the volume expansion, whereas the liquids and the gases they experience only the volume expansion. Now thermal expansion along one dimension in the solid objects is called the linear expansion. Thermal expansion along the two dimensions in solid objects is called the superficial or the areal or the area expansion, and the thermal expansion along the three dimensions of a substance is called the volume expansion or the cubical expansion. In the case of solids, we can experience the linear, superficial and the volume expansion, whereas in the case of liquids and gases, only volume expansion is seen. Now, in the session number 5, we have seen that the change in the length of a solid object is given by, that is delta L is equal to L naught alpha delta T, where alpha is the coefficient of linear expansion, L naught is the original length and delta T is the change in the temperature. And delta A is equal to A naught to alpha delta T, where alpha is again the coefficient of linear expansion, A naught is the original area and delta A is the change in the area and delta T is the change in the temperature. Similarly, delta V was equal to V naught into 3 alpha into delta T, where alpha is the coefficient of linear expansion and V naught is the original volume and delta T is the change in the temperature and delta V is the change in the volume. So we have in the session number 5 we have derived these means we have discussed about these equations in which the change in the length, area and the volume was described in terms of the coefficient of linear expansion only. But in this session we will be discussing about the change in the length, not only in terms of the coefficient of linear expansion but also in the terms of the coefficient of superficial expansion, that is beta, and the coefficient of the volume expansion or the cubical expansion, that is gamma. So delta L is equal to L naught into alpha into delta T, whereas delta A, which is the change in the area of a solid object, this is equal to delta A naught into beta into delta T, where beta is equal to 2 times of alpha. And what is beta? Beta is the coefficient of superficial expansion. Now here similarly delta V is equal to V naught into gamma into delta T, where gamma is equal to 3 alpha and gamma is the coefficient of volume expansion. So from these two equations we can say that beta is equal to 2 times of alpha and gamma is equal to 3 times of alpha, or we can say that alpha is equal to beta upon 2, which is equal to gamma upon 3. So this is a very important relation which every one of you must remember. So now after calculating the value of these the change in the length, the change in the area and the change in the volume, we can also find the final length, the final area and the final volume of a substance. So the change in the length of an object, a solid object, the final length of a solid object after the change in the temperature, that is delta T, can be written as L naught in bracket 1 plus alpha delta T, where alpha is the coefficient of linear expansion and delta T is the change in temperature. And how we have got it? This LF is the final length of the solid object, which will be equal to the original length plus the delta L. So if I add this original length and this delta L, I will be getting this expression. Similarly, the final area of a solid object can be written as A naught in bracket 1 plus beta delta T, because AF is equal to A naught plus delta A. Similarly, the volume, this final volume can be written as V naught in bracket 1 plus gamma delta T, because final volume is equal to V naught plus delta V. So when we add both this V naught and delta V, we will be getting this expression. So these are the 3 important equations which we will be using in our further sessions while solving the numerical problems. Now, we also know that when the temperature increases, the density decreases, and this decrease in the density can be given by this formula, that is, this rho is the density, this is the final density, which is equal to the initial density divided by 1 plus gamma delta T, where delta T is the change in the temperature and gamma is the coefficient of volume expansion. So this is also a very, very important formula and needs to be remembered all the time. So this was a short description on the thermal expansion of solids, liquids and gases, and some of the important formulas which needs to be remembered by all of you. Now, as we have just studied that liquids have got only the volume expansion and the gases also have got the volume expansion. Now, in the case of liquids, there are two types of expansion. One is called the delta V A, which is called the apparent change in volume, and delta V R. This is the real change in the volume. Okay. Now, delta VA and delta VR, they are related to each other by the equation, that is gamma A is equal to delta VA divided by original volume into the change in the temperature, and gamma R is equal to delta V R divided by V into delta T, where delta VR is the real change in the volume of the liquid, and delta VA is the apparent change in the volume of the liquid, V is the original volume, and delta T is the change in temperature, and gamma A is the coefficient of apparent expansion. This is the coefficient of apparent expansion. And this gamma R is the coefficient of real expansion. Now, this gamma R and this gamma A, they are related to each other by gamma R is equal to gamma A plus gamma V, where gamma V is the coefficient of volume expansion of the vessel in which the liquid is kept. This is the coefficient of volume expansion. Volume expansion. So gamma R is equal to gamma A plus gamma V. So gamma V is the coefficient of volume expansion, or this can also be written as gamma R is equal to gamma A plus 3 times alpha, because alpha is what? This is the coefficient of linear expansion, and we have already studied just now that alpha is equal to beta upon 2, and this is equal to gamma upon 3. So gamma can be substituted by 3 times of alpha. So I have written it here also. So gamma R is equal to gamma A plus 3 times of alpha also, where gamma R is the coefficient of this real expansion, and gamma A is the coefficient of apparent expansion, plus this gamma V, which is called the coefficient of volume expansion, or 3 times of alpha, where alpha is the coefficient of linear expansion of that particular vessel. So we can here say that this gamma A is equal to gamma R minus 3 times of alpha. So we can here, from this relation, we can see that this coefficient of apparent expansion is dependent on the coefficient of linear expansion of the vessel in which the liquid is kept. If this value is more, then the coefficient of this apparent expansion, that is gamma A, its value will be less. So so there in the case of liquid, there are two types of expansion, that is the apparent change in the volume, and second one is the this real change in the volume, and these two are defined by these two relations, that is gamma A is equal to delta VA upon V into delta T, where gamma A is the coefficient of apparent expansion and gamma R is equal to delta VR upon V into delta T, where gamma R is the coefficient of real expansion, and which is given by delta VR upon V into delta T. And these two are related to each other by this equation, that is gamma R is equal to gamma A plus gamma V, where gamma V is the coefficient of volume expansion, okay? And this can be also written as gamma R is equal to gamma A plus 3 times of alpha. Now let us come to the thermal expansion of gases. So in the case of gases, there are two types of thermal expansion. One is called the coefficient of this volume expansion at constant pressure, which is given by alpha, and this is given as delta V upon V multiplied by delta T. So here alpha is what? This is the coefficient of volume expansion at constant pressure. This is the coefficient of volume expansion at constant pressure. At constant pressure. And there is one more relation, that is beta is equal to delta P upon P into 1 upon delta T, where beta is the coefficient of pressure expansion at constant volume. Now here delta P is what? This is the change in the pressure, P is the original pressure, delta T is a change in the temperature, and beta is the coefficient of pressure expansion. So alpha is the coefficient of volume expansion at constant pressure and beta is the coefficient of pressure expansion at constant volume. So from here we can find that delta V will be equal to alpha into V into delta T, and beta will be equal, delta P will be equal to P into beta into delta T. So from here you can also find the final volume, that is final volume Vf can be written as V plus, that is V plus alpha V into delta T, so V can be taken as common, 1 plus alpha delta T. Similarly, the final pressure, that is Pf, can be written as P common 1 plus beta delta T. So in the gases there are two types of in the gases there is only a volume expansion, and the volume expansion means these are of two types. One is the coefficient of volume expansion at the constant pressure, and the other one is the coefficient of pressure expansion at constant volume. So thank you very much for joining in this session, and in the next session we will be taking up a couple of questions based on what we have studied in this session. So till then, have a nice day. Bye.